In section 9.10, I might give you the function f of x equals sine x, and I might ask you to tell me the power series, also called the Taylor series, centered at x equals pi over 4. How did we find a Taylor series or a power series for a function?
F of 0 plus f prime of 0 times x minus c, f prime of 0 over the n factorial.
Okay, so what you're giving me the power series centered at 0. All right, so in general, our power series is going to be f of x is f at c, where c could be any number. You were giving me 0, which would be also called the Maclaurin series, plus, then we had f prime at c times x minus c divided by 1 factorial. And then what was the next one?
F double prime at c over 2 factorial.
X minus c squared. And we would keep going. Then it would be the third derivative divided by 3 factorial, x minus c cubed, plus on and on forever. Okay, so what I need to do to find the power series centered at pi over 4 is I need to start with my function. I need to take the derivative, the second derivative, the third derivative, fourth derivative, fifth derivative. Hopefully I'll see a pattern develop. And I'm going to need to take and plug pi over 4 into all of those derivatives. All right, so I have sine x. What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. What's the derivative of negative sine? Negative cosine. What's the derivative of negative cosine? Sine. And then this one's just going to cycle back around on itself, isn't it? So I think that's plenty of derivatives. So that's 1, 2, 3, 4 derivatives. After that, I'm going to get the same thing over and over and over again. Now I take each of these and I plug in pi over 4. What's the sine of pi over 4? Square root of 2 over 2. What's the cosine of pi over 4? Same thing, square root of 2 over 2. What's the negative sine of pi over 4? Negative square root of 2 over 2. Next one is negative square root of 2 over 2. And then we go back to square root of 2 over 2. Okay, so here's my answer. My answer is sine of x is equal to f at pi over 4, that's square root of 2 over 2, plus f prime at pi over 4. So here's my derivative, that's the next line. That one's also square root of 2 over 2. Divide by 1 factorial. Of course, 1 factorial is just 1. That doesn't change anything. X minus pi over 4. What's my next one? Minus square root of 2 over 2 divided by 2 factorial. X minus pi over 4 squared. Next one. Minus square root of 2 over 2 divided by 3 factorial. X minus pi over 4 cubed. Plus dot dot dot. I guess that's enough.
Is it supposed to be pi over 4?
Oh, sure. I don't know why I wrote just a 4. Could you write this that way? Can you write that as a summation? Well, most of it's real easy. I think you would agree they all have a square root of 2 over 2. They all get divided by what? N factorial. They all have a x minus pi over 4 to the n. What's the hard part on this one?
The signs,
The signs. Yeah, what's hard about the signs?
they're not really alternating.
They're not really alternating because you get 2 positive ones, then you get 2 negative ones, then you're going to get 2 more positive, then 2 more negative, 2 more positive. How do you write that? Well, I don't know either. I was hoping one of you guys would be smarter than me. My point is, it's not always easy to write things using this summation notation. So I need to have a -1 to a power, but I'm not sure what to write for that power to make it so that I get 2 positives, 2 negatives, 2 positives, 2 negatives. I honestly don't know how to do that. There's probably a way, but I'm not aware of it. Okay? So sometimes it's quite easy to write these in summation notation, like all these famous ones that we were looking at the other day. It's pretty easy to write all these using a summation notation, except for the last one. The last one, the binomial expansion, is kind of hard. Sometimes when you write down a power series, not so easy to write the summation notation, and I think this one's a good example. Not sure what to do with that -1 to a power. Questions on that? Okay, how about if I ask you for the power series of f of x equals sine of x squared centered at x equals 0. How would you find the power series for sine of x squared centered at x equals 0? Take the derivatives. All right, so we have f of x equals sine of x squared. F prime of x would be cosine of x squared times 2x. And this gets ugly in a hurry, doesn't it? I mean, just for example, what's the second derivative? I've got to use the product rule. So I leave the cosine alone, cosine of x squared. Take the derivative of that one, that's a 2. Plus, leave the 2x alone, take the derivative of this one. Negative sine x squared times 2x. I really don't want to take the third derivative, do I? It's ugly in a hurry. There's a better way. Anybody know the better way? Wolfram alpha would be a good way. There's an even better way than that, believe it or not. Better than Wolfram alpha. We figured out the other day the power series for sine x centered at x equals 0. Anybody remember what the power series for sine x centered at x equals 0 turned out to be? It had the odd powers and it alternated. So this one was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus, and it went on forever. This one was easy to write as a summation. This is a sum from n equals 0 to infinity. -1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. We wanted just the odds. So how does that help us Find the power series for sine of x squared.
Square all the x's.
Wherever there's an x, plug in an x squared. That's exactly right. So once you have one power series for a function, finding another power series for a related function is very easy, usually. We just plug in. So when I plug in x squared, I get x squared. Minus. What do I get when I plug in x squared there? What's x squared cubed? X to the 6 over 3 factorial. Plus x to the 10 over 5 factorial. Plus x to the 14, or minus x to the 14 over 7 factorial, plus da 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 da. Can you write that in summation notation? You're going to have minus 1 to the n. What are you going to have there?
X to the 4n plus 0 to
X to the 4n plus 2 divided by,
so it will still be 2n plus 1.
it's still going to be 2n plus 1 factorial, isn't it? That hasn't changed. So all you did is you took x squared and plugged it in. When you take x squared and plugged it in there, you multiply your exponents. 2n plus 1 times 2 is 4n plus 2. Questions on that? Okay. How about a power series for, I don't know, how about g of x is e to the x cosine x, and again I want this one centered at 0. What was the power series for e to the x again, centered at 0? Anybody remember? It had all of them and it did not alternate. So that one was just 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and it went on and on forever. And I want to multiply that by cosine. What was the power series for cosine? The evens alternating. So it started at 1, and then it had minus x squared over 2 factorial plus x to the 4th over 4 factorial, and it went on and on forever. All right, so now just consider multiplying these together. If I multiply these together, the only number that I'm going to have is 1 times 1. What's 1 times 1? 1. What about x to the first power? How am I going to get x to the first power? Thinking about taking these and multiplying by all of those. The only x to the first power is going to come from this 1 times that x. So I'm just going to have a plus x. How about x squareds? I'm going to have this 1 times this thing with an x squared. And then I'm going to have that 1 and that thing with an x squared. And what's going to happen to those two things? They cancel, because this is a minus x squared over 2 factorial. This is a plus x squared over 2 factorial. So we're not going to have any x squareds. Those cancel out.
They multiply by themselves.
But when I multiply by themselves, x squared times x squared gives me a x to the 4th. So that won't give me an x squared term, will it? So there's not going to be any x squareds. How about x cubes? An x cube will come from this x and that. Correct? That would give me an x cubed. And then I could also do this x cubed with that 1. All right, so for x cubes, I'm going to have a minus 1/2, a 1 over 2 factorial, and then a plus 1/6 x cubed. All right, let's do one more term, and then I think that'll be enough. How about x to the 4th? Where am I going to get my x to the 4th from? I'm going to have the 2x squareds, and then I have a 1 times an x to the 4th. I can't do x times x cubed because they're in the same one. But I am going to have a 1 and an x to the 4th, an x to the squared and an x squared. But then don't forget there's really another x to the 4th right there times that 1, isn't there? So how many x to the 4th pieces are there going to be? 3 of them. So we're going to have this one. That's going to give me a 1 over 4 factorial. So that's 1 over 24. And then we're going to have this one. That's a 1/2 times a negative 1/2. That's a negative 1/4. And then we would have this one, which would have an x to the 4 over 4 factorial times 1. So that would be plus 1/24. X to the 4th plus dot dot dot. And you could continue that on as long as you wanted to and get a power series for multiplying two functions together. Now, is it practical to do it a whole lot further? Not by hand, not practical. But you could, of course, get Wolfram Alpha or a computer to do it. Questions on that?
Could we write the answer in like a sigma notation for each part?
Write each of these in sigma notation?
Yeah.
Yeah, I suppose you could, but then it would be difficult to tell how are you going to get the x, how are you going to get the x squared, how are you going to get the x cubed. Because really what we have to do is we have to distribute. Technically what we have to do is take this 1 and multiply it by every single term. And then take this x and multiply it by every single term. You're really doing a big distributive property. All right, how about my last question for the day? Approximate the integral from 0 to 1 of e to the negative x squared. Other than using your calculator or using Wolfram Alpha or some other form of brilliant technology, how could you approximate that integral? Well, this is a very famous function. It's a very famous function in the sense of this is one of the ones that's always used as an example for you can't use the fundamental theorem of calculus. Because e to the negative x squared does not have an antiderivative. So what do? You use power series. What's the power series for e to the x again? 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and it goes on and on forever. So what's the power series for e to the negative x squared? 1 minus x squared plus x to the 4th over 2 factorial?
Would that be negative?
Which one, this one?
Yeah.
No, this one would be positive because I'm taking negative x squared and plugging it in. And when I take negative x squared and I square it, when I square a negative, it turns it into a positive, so this one's going to turn into an alternating series. When I take negative x squared and plug it in there, I get negative x to the 6th over 3 factorial plus on and on and on. What's then the integral of e to the negative x squared dx? Well, what's the integral of 1? X. Minus, what's the derivative of x squared?
Negative x cubed over 3.
Minus x cubed over 3. Plus, what's the antiderivative of x to the 4th over 2 factorial? X to the 5th over 10, 2 factorial times 5, minus x to the 7 over, I'm just going to leave it as 3 factorial times 7, plus on and on and on. Okay, so now how do I answer this question? How do I approximate this integral? Well, I come down here and I decide, how many terms do you want to use? You want to use 2, 3, 4, 5, 6, 7, how many terms do you like? Well, there's my first term. You like 3? All right. So the integral from 0 to 1 of e to the negative x squared dx is approximately, if I'm going to use 3 terms, I'm using those 3. I'm going to take 1 and plug it into that. So that's 1 minus 1/3 plus 1/10.
Can you move that up?
So all I did is this is my antiderivative, so I plugged the top number in, minus, I plugged the bottom number in. What do you get when you plug 0 into that? 0. So that's 1 plus 1/10. What's 1 plus 1/10? 11/10 minus 1/3. That's 33/30 minus 10/30. So our approximation is 23/30. Just for fun, math integral of e to the negative x squared comma x comma 0 comma 1 How accurate was our answer? Not bad for only using 3 terms. How could we get a more accurate answer? Use 4 terms, use 5 terms, use 6 terms. What if we added just one more term? One more term, we would have to subtract 1 over 3 factorial times 7. So what if I take 23 over 30 and I subtract 1 divided by 3 factorial is 6 times 7? I guess I could have done that in my head and called it, what's 6 times 7? 42. How much more accurate does that make it?
One more place.
It gave us another decimal place, gave it pretty good. Once again, when I type this function integral into my calculator, how do you think my calculator is doing it? It has some sort of approximation algorithm. Again, my guess is the approximation algorithm it's using is not exactly this. My guess would be techniques have been developed which converge much more quickly, but this is the basis behind the computer programming that's going on behind the scenes. It's using some sort of approximation algorithm. I don't know exactly what it is. Something similar to that, though. Questions on that?